When studying exponential growth and decay, the functions itself, so which typically may happen in grade 11 or you might be doing it somewhere else, you're going to run into numerous examples which actually illustrate the whole concept of exponential growth and decay, which is nice because most of the time in math we don't really see a huge amount of applications until maybe later on. And then you can't really draw the connection between all the stuff that you did with math and then the actual real world and some examples that it might apply to. Now, with exponential growth and decay, this actually should be relevant very, very quickly. And I hope that your teachers show you some of these examples as you're studying these exponential functions. Now, the exponential function itself, so if you kind of recall, it starts off, one of the simpler ones that you have typically will look something like this: a and then b to the x. And then depending on what b is, so that base, if it's between 0 and 1, we know that the function actually decays. And if the b is greater than 1, then we know that it's an exponential growth. So that's something that happens. I can put up a link up above there if you like, if you want to review that. Now, let's apply this concept to some of these examples. And I'm going to purposely take some examples. So for example, in terms of maybe possibly investing some money, which is very relevant. At some point, you're going to study maybe compound or compounding. Okay, in terms of population growth, sometimes maybe like viruses, because they expand, unfortunately, typically on an exponential kind of trajectory. And you might have some decays as well, okay, where something is actually decaying. Now, this first example that we have is taken, and it's with regards to money. And I purposely made it with money just so that hopefully it makes sense to you. And I'll try to draw the connection, and we're going to come up with the actual function and then answer the question itself. And you will slowly see that it's actually not that hard. All right. So if you started with $1,000 investment in a company that grew in value at a rate of 10% per year, then how much would you invest, how much would your investment grow to after 25 years? All right. And then let's just create this function. Sure, we're going to round and so on. Now, you see these words grow in here. So it will have something to do with growth. Now, how in the world does this relate to exponential growth and in terms of the function, which looks like a kind of b to the x? So if you remember, okay, so in terms of growth, instead of writing the function in the format that I did above there, we can write the function in this format: 1 plus r, okay, to the x. And then, the x is going to be, in this case for us, the input, it's going to be the number of years that we're investing for. So sometimes people like to put n instead of x, okay, for the number of years. And I mean, we can do that. It doesn't really matter what you use as that variable. But what is key is what this a is, and then we know that, okay, in terms of the exponential growth, we're assuming that this r is going to be greater than 0, right? Now, that r is actually the rate of growth, in this case, the rate of growth of the money, which is telling us it is growing at 10% every single year. So how would this look like? Originally, at least for this question, I'm going to try to show you that in the beginning, okay, so what you have is you kind of have, okay, this $1,000 that you're carrying out, and that is your starting point. So I'm going to write 1K, which is $1,000. And then it says, in 1 year, it grows 10%. Now, what is 10% of this $1,000? Okay, so if we take 10%, so that would have been 0.1, because 10% as a decimal is that. And then we would multiply it by the $1,000. And what we would get is we would get $100. So after 1 year, our original amount here, so this right here, okay, so I'm going to duplicate it. Now, that's not what I wanted. Let me move this over. So after 1 year, you have, the question can be, okay, so how much money do you have now after 1 year if it has grown by 10%? Well, it's going to be your original amount, which is the 1K, plus the actual interest, which was $100. which really turns out now to be, 1.1K, because that's what 1,000 plus $100 is. Okay, that K just represents 1,000. We typically do that when we're talking about money, but not even money. Okay, so this K that you see there just means 1,000. Now so obviously it must be a little bit bigger, all right? So it can't be the same. It's going to be just slightly a little bit bigger. So because of the fact that we had this interest. Now this interest, so whatever it was, okay, so it was some value which we have added on top, okay, and now we have 1,100. And now that was after 1 year. Now after 2 years, well, your starting point is different, right? So what you have is you have 1,100, and now you're going to take 10% of that, which is going to be now $110, because that's what 10% of 1,100 is. So what you're noticing here is you're going to see, okay, that, oh, okay, well, I'm going to have now more money, okay, after 2 years. And then again, I'm going to have more money, okay, after 3 years. And this trend continues, where all we're doing really is we're just adding 10% on the value that we had in the past. And in this question, it says, so how much did it go for? Or how much did it grow to after 25 years? Well, you surely wouldn't want to be drawing these graphs and then doing these calculations individually, adding 10% to the past year every single time for 25 years, right? Which means in our case, this would be for 25 times. That would be really annoying to be able to do that. So, what actually happens? Well, what happens is originally you start with $1,000. That's what you start with. Now, what you're actually doing is you're adding the 10%, which is right here. And that 10%, all that it is your original amount, okay, which would be 1,000 times 1, plus the 10%, which is 0.1. And notice that that is equal to 1,100. That was after just 1 year. Now, after the following year, you take this amount and this amount, which is 1,100. And again, what you're going to do is you're going to add 10% to it. Okay, so you're going to be multiplying it by 1.01. And then you continue this pattern year after year, where you're going to take that original amount, whatever that might be. Now, in this case, would have been 1,210. And again, you're going to be multiplying it by 1.01 to get the following year. And you keep doing that, right? And as I said, you don't want to do that for 25 years. And in math, we notice that there's some pattern here, because all we're really doing is we started with 1,000, and then next, what we do is we just keep multiplying by the 1 plus 0.1, which is adding 10%. Notice, okay, within here. So after 3 years, what we had is, so if you wanted to know what this value really was, it is simply just 1,000 multiplied by 1.01. But now notice you've done it once, twice, 3 times. And this is where the exponential comes in. And if you tie it back to our functions, well, this looks exactly like this, right? Where this A is basically your starting amount. That's what your A is in exponential functions. That's what you start with, right? That's the y-intercept at x is equal to 0. So in this case, it's our starting point for our money of investments. So that's our $1,000. And then this 1 plus r, the r just simply means, okay, so what is it growing at? What percent does it grow at? Well, it grows at 10%. And the only really trouble is just changing the 10% back into a decimal number, which is 0.1, because we're dividing by 100. And then this x right here, so what it is, this is representing is just, this represents just the number of years that we have. How many years have you invested for? And that's why I say, typically we may not write it as x. Sometimes people write it as n, and n just means number of years. So this is not a very bad question at all, because once you see this once, twice, 3 times, you notice that, oh, okay, well, what's your initial investment? Well, my initial investment within here, so my function really, so I'm going to write n, okay, instead of writing x, because it's more relevant, so number of years. So the function for us, okay, for this investment would become $1,000, which is your initial amount. So that's your A. Now my B that I have, which is 1 plus, which is the 10%. And then this is going to be raised to the N. And now, so this is your R. Okay, so this is your R, which is your rate, okay, of growth. And the growth just simply is with this plus. And that's what you will remember from exponential functions, okay, in terms of growth. That's our actual setup. And now you can find out at any point that you like, you know, what this has actually grown to. You know, do you want it after 1 year? So you can set N equals to 1. Do you want it after 2 years? Do you want to have it after 2.5 years? What do you want to be? You know, how long are you waiting for this investment as it keeps growing at 10%? And, you know, we call this compounding because it just keeps, okay, multiplying, okay, by the same thing over and over and over again. And so they asked us, okay, so in this question, what they asked us was, what was the growth after 25 years? And if I wanted to know that, let's say, no, so this is 25, then I can just go ahead and then compute it. So it's not a big deal, okay, to try to compute it. So it's 1,000 multiplied by, now 1 plus 0.1, which is going to be that. And it's raised to 25. And notice that's actually quite a big amount there. So it's 10, 8, 3, 4, okay, 0.7. And since it's money, we're going to be rounding to the cent. So that $1,000 is almost $11,000 that we had. And that's what actually happens within here for this particular question. That's your function right there. And now here I think it also says, you know, create a function. So we did, and then plot it on a graph for all the years of investment. Okay, so we can plot this. So let me pop up decimals. All right, so here is decimal. So I'm just plotting this function now. So we're starting at 1,000. That's my A. My B is 1.1. Again, remember, if B is greater, right, your base is greater than 1, it's going to be an exponential growth function. It's just to blow up. Now, because it's money, we don't really kind of go on the negative side in terms of the number of years. So I'm going to put a restriction. So I'm putting braces here. And I'm going to restrict this in between. Sorry about that. Okay, so my N, I'm going to restrict between 0 and 25. This is kind of what they wanted so that we can see. So that's after 1 year. And notice, you know, here, if I go all the way up here, that's my 10,000. It's kind of faded there. 834, you know, 0.7. I mean, it doesn't round to the penny for us because it doesn't know it's money. But that's exactly what happens. And notice on this curve, so let's say it doesn't matter how many years have gone by. So, you know, if as long as I'm just going on this curve, so let's say, you know, after approximately 10 years, so it's 10.1 years, this would have grown to $2,618 and some, you know, 58 cents or something like that. And that's what this is telling you. That's the exponential growth that we have for this example. Let's take a look at another example, which I'm not going to go into a huge amount of detail in explaining. I hope that the explanation here kind of makes sense to you. Once you grasp it once, it's so much easier to apply it to really any applications, not just money. So here is, you know, another example, and it's not money at all, but it's the same concept. So it says in a town of 1,500 people, the growth of the population occurs at a rate of 3% annually. So the word annually means per year. Now, that might be common, right? You might have a smaller town and it might be growing. Maybe there are immigrants coming in. There's also babies being born and so on. So it might be growing So now, how many people would the town have after 15 years of steady growth? So this is growing at this 3%. And now the question is, okay, so how many, people would be here? And now, so round your answer to the 1, which makes sense. I guess it's people. We don't want to cut them off, so we don't want to have any decimals. So we'll cut it off at the whole numbers. And then create a graph and plot the population function for 30 years. What can you conclude? Well, what we can conclude is if it's growing, we know it's going to blow up. We can conclude that. But without now going into as much detail as I did with the other question, because all of these exponential questions, and again, I'm going to use n here for the number of years, and population, so maybe, instead of using f, I'll put p, which is going to be population that we have. So what's the population after a certain number of years? Now, what do I need? I need, what are you starting with? Right? Because that is my y-intercept. That's your a. So we know it's going to look like this. It's going to be a, 1, it's growing, so 1 plus r to the n. That's my exponential function. Now I need to figure out what a is. Well, my a is my starting point of the number of people. That's at year 0, when n is equal to 0, I'm just going to have my starting point. And then now what I need in here is I need to know what is growing, what is the rate of growth. But the rate of growth they give us, it's 3%. So this is going to be 0.03. So really the only thing is, please don't forget that your r is typically a percent of some kind. So you're going to have to change it to a decimal or a fraction or whatever it is that you want, but don't keep it as a percent if you're going to input it into your function. So this is my function now, and here I'm going to have 1.03, okay, and then n. That is my function. All right, here is your starting point. Here is your b. Your b is actually greater than 1 again, so that means it's going to blow up on us at the rate of 3% per year, and then n just simply in this case just would represent the number of years. So what is it? Now they're asking me after 15 years. Well, then that's not a big deal. So I can just input all of this in. I have 15 years of growth, which is going to be just some number. So 1500 multiplied by, and I guess it's 1.03 to the 15. All right. So this town, okay, would have 2,330. Okay, let's round it to the whole number. So approximately this many people. That's what it would have. And that's your exponential growth. Now let me plot it on decimals again. And there you have it. All right, so that's over the 30 years that this is what would happen. So we're going to be starting off here at 1,500, and then the population is just going to slowly grow, okay, as we keep going. Now, slowly, it's still exponential, but it's at 3%. And if we wouldn't cap this at 30, it's at 30, so I guess at 30 point, I'm actually curious what would be the population here. At 30, okay, so it's already 3,600. Now, if the town continued, right, to grow for much longer than that, let's say if I put 100 here, so what you notice is, now it definitely starts to look like an exponential, right? It really just starts to skyrocket. Why? Because that 3% just keeps adding on to the previous year, because it's 3% of the previous year, not always from the start. And that's why it starts to look like this exponential, which is amazing, right? And in terms of money, like if I go back to the other question, if I had money here, if you didn't keep it for, 25, notice what happens now after, if I kept it for 35. Well, all of a sudden now that money, that original 1,000 starts to look pretty good. It's, it's 30,000. So imagine you put away, $10,000 or something like that. So those are exponential growths that we have within here. And I also want to give you another example, which is kind of relevant within here. unfortunately relevant, but you know, a lot of people have struggled with this. So, you know, this video is being made in 2021, where, you know, over the last like maybe almost 2 years, you know, we were struggling with the coronavirus. Some countries did better than others, but you certainly do have viruses that spread around in the population in an exponential growth. And here is an example, for instance, and I'll show you, you know, the power that happens, you know, and if you allow these viruses just to keep spreading. So a virus has taken over a city, growing at a rate of 8% per day. So here's my 8%. That's going to be your R. Initially, only, you know, 12 travelers. You know, so let's say this was your city. You know, you 12 travelers come in. And, you know, maybe like New York or, you know, somewhere else. Okay, LA or Toronto or I don't know. Okay, anywhere. Maybe Berlin. Now, 12 travelers, that's all. Which seems kind of tiny when you have, you know, maybe millions of people in a city, were infected with the virus and nobody noticed, right? And it just kept carrying on. So if nothing was done to prevent the growth of the virus, then how many people would be infected after 150 days, right? Notice it says it's 8% per day now. It's not per year, it's per day. Because per year it would still kind of just trickle off and then it would slowly kind of just creep up. But, you know, if it was 8% per day, well, now this is becoming a little bit of a headache. Okay, and then now what happens after 150 years? So I think you hopefully, and now again, so this is the virus. I'm going to put V for virus to make it more relevant. N is the number of days this time around. This is going to be my A, 1 plus R to the N. So in my A, what am I starting with? My initial starting point. So in this case, I only had 12 travelers that had it. 1 plus 0.08. And then here's my N. Now, they're saying 150 days. All right? So, I mean, we can compute this. Wherein we can, you know, put 150 here. But instead, what I'm going to do is, because it says graph it, let's just graph it. And then see this, the exponential growth of this virus over time. And I hope that this, you know, will now come back at you. Actually, so here we go. So this is the virus one. So let's put it in here. Equals to, so only 12 plus, it's growing at 8% per day. Now this is all per day, by the way. And so within here, so what we're going to try to do, actually let's not even block it up. Okay, and let's see what happens. Okay. I guess the only restriction that I'll put is I'll put N, which has to be greater or equal to 0. Okay, because we're not going to go into negative days here. And notice, so this is your virus, right? So 5 days, right? Like notice, so 10 days, nobody really notices. You know, 20 days kind of crosses over 50 there. That's how many people have. Okay, so not a big deal. But now, as you keep going, like look what's happening here. It's just exponentially blowing up. And in fact, you know, if I go here to 150 days, look, it's way off the chart. So I actually have to zoom in, okay, and just keep going. And this is going to scare you, you know, like after 150 days. I'm going to keep it like that. Let me do this, okay, and just keep going, you know, keep going. I mean, this is getting pretty crazy, right? Like thousands and thousands. All right, I think we finally crossed it. There we go. Okay, 150 days. Okay. Right, which is somewhere around there. Notice it says 150, so just over, but somewhere around there, where we're going to 150 days. There we have it. Look how many people. That's over 1,238,068 people. It's nuts. But that's what exponential growth does. Notice in the beginning, doesn't seem like much. It doesn't seem like to grow, okay, you know, 200s and so on. But then it just starts to skyrocket, okay, if you allow it. That's the application of these exponential growth functions. Now, what about exponential decay? You know, are those any different? Well, the answer is no, they're not different at all. And in fact, the only difference, if you remember, right, from the exponential decay, again, you can go back to the beginning of the video where I kind of asked you can watch the link there, where I introduced this exponential growth and decay function. The only difference when you're reading these questions with exponential decay, nothing changes. For instance, here it says a city of 2.5, by the way, the capital M means million. So I have a city of 2.5 million people, and it's decaying its population. Maybe people are leaving, which happens, right? Maybe it was a popular city. All of a sudden something happens. People do start losing jobs. So people start slowly leaving. So here it says, annually, okay, we are decaying. So people are leaving at a rate of 3.5% annually. If this rate of decay continues for 12 years, then what population would remain, right? So how much population would you have? Round to the 1, and then create a function of this scenario and plot it on a graph for 20 years. So when you're studying these types, now again, it's population, so I'll put P, but maybe what I'll write first is I'll just kind of remind you, is that for our exponential functions, which kind of, looked like this, we knew that if B was between 0 and 1, so if it was less than 1, we would have a decaying function. That exponential would start to decay and get closer and closer towards 0, right? That's what would happen. Now, this we introduced as kind of this B, we said 1. Exponential growth was plus R, but decay is minus because it's decaying at a certain rate. So this is what our function, general function for exponential decay looks like. The key thing here is this is minus and that R is between 0 and 1. All right. So that it makes this B, okay, because if you're going to subtract R, okay, it's going to fall somewhere between 0 and 1, and then we have our B between there, so that we're going to be decaying. The A, again, still just stands for, what are you starting with? So for this question, I'm going to, instead of using F, I'm going to use P again because it's population. So let's say P of N. So my starting point is 2.5 million. Now, how you write it is up to you. I'm going to just write it in full so that it really stands out for us. 1 minus, now what is it decaying at? It's decaying at 3.5%. So, please divide it by 100 to change it to decimal. And then, your X, now I'm using N for the number of years. This is now my function. And now this function in general, okay, so this right here, if you do that subtraction, it's going to be 0.965. And so that's going to be that to the N. And notice it's less than 1. Which means it's going to eventually start to decay and go to 0. Now it says after 12 years. So if I did this, I'm going to clear this out and put this, so 2500, 1, 2, 3, multiplied by, I guess, and I'm going to put it in brackets, okay, just so that you see the whole thing. And this is after 12 years. So after 12 years, well, that's interesting. It actually shrinks almost by a full million. So this is rounded, all right? So rounded to the 1 there. That's what the answer is after 12 years. Now it says to plot it for 20 years. So let's see it as if, when we're plotting this. All right, so here you go. So I put the function in there. So notice the 1 minus, and right away, notice that it just starts to decline. And, if we let this go longer than the 20 years, you would see that if it continues to decrease at 3% every single year, and you extended that function, it would just continuously and just drop off towards 0. That's what happened. So this is an exponential decay application with population that you have. I have one more example, so I know that I'm pushing you to the limit because it's a pretty lengthy video. But for those who want to learn, you can hopefully see these things and understand them. So here's another application. So here's a tumor, and it has a mass of 670 grams. And so notice, it's not just population, it's not just money. You know, this can be, you know, in healthcare with cancer or anything else, you know, these things. I mean, I made this example up, but it's very applicable to numerous fields. You know, in engineering, it's a huge thing to understand exponential functions. So if anybody's going to go in that direction, you know, I'm a little biased because that's what I studied, okay? So that's my background. And in systems control, you know, you may be watching this as someone in grade 11, you know, might not have any idea what that is, but, you know, all our kind of controllers that we have utilize exponential functions quite a bit. So a tumor of 670 grams shrinks at a rate of 50% per day after successful chemotherapy session. How many days would it take to shrink the tumor to a size of 1 gram? Create a function based on this scenario and plot it to see the decaying process for 20 days. Okay, so now instead of finding out, because in all our previous examples we were always finding out what happens after a certain number of days or a certain number of years, here they actually tell us that, you know, how long will now it take, you know, so how can we do that? And as you progress through your math, you're going to be able to know the tools to use to be able to solve something like this, but I guess we're going to do it graphically because that's what it asks us to do. So let's set it up, okay? So, you know, you have a tumor. So this is a mass, right? 670 grams is a mass. So I'm going to, instead of writing, you know, P for population, I'll write M. And then, you know, this is still days. So M of N, okay? So mass after a certain number of days. So what do we have? Well, we know what initially the tumor, okay, so the mass of that tumor was, which was 670 grams. Now, it is decaying, okay, at 0.5 like this. So this is what we carry, and that means, so this is going to be to the N. We have 670, you know, 1 minus 0.5, I guess that's a half, okay, or 0.5. Okay, so I'll write it like this. You can write 0.5 if you like. And now the question is, we want to know how many days. Now, if we want to know how many days, we actually have to solve for this N. And they're asking us, so here, notice, you know, how many days would it take to be 1 gram? So we want to know, you know, what is M, okay, at what particular day will it be equal to, you know, approximately 1 gram? That's what we want to know. So what are we doing? Now notice this function, okay, if you've thought of it as a function, because it's M, you know, is equal to 1 gram. If you plot that, that's just a straight line, right? And here is where you're starting to see, you know, how you utilize these things and why these functions are sometimes important. So M is equal to 1. It's like a flat line, okay, which goes through, okay, if you think of the y-axis as your mass, okay, and your x-axis as your N, which is the number of days that you have, then when you say M, you know, the mass is equal to 1 gram, that means you're just plotting a flat line. So that's what I'm going to have. So what's going to happen is, you know, we're going to have, I'm just going to sketch it for you first. Say this is your N, this is your mass over here. We're going to start at 670 grams. Now we know it's going to be decaying like this, right? Because that's what an exponential function does. By now you should know that without even graphing, because the half, the 0.5, is between 0 and 1. That's your B. So it's going to decay. And now you want to get it all the way down so that, you know, like it's basically 1 gram. So here I'm going to do it in a different color. So, you know, I mean, it's hard to do here, but you have a line in here at 1 gram, and you're trying to find really the intersection between these 2 points. And that intersection is going to be, okay, how many days did that actually take to get to that 1 gram? Okay, so I hope that makes sense. Now, they put 1 gram here, but they could have chosen anything. So let's plot this just so that we can see it. And then we're going to pick off the answer from the plot. So here is my M of N equals, so we started at 670 grams. 1 minus 0.5 to the n. So I'm going to leave it like that. I guess the only restriction I'll make, whoops, is, it has to be, can't go back in time. So it's going to be positive in this way. So that's what we have there. I'm going to have to stretch this and get back here to reality in terms of the numbers. Okay, so there we go. Okay, that's our graph. And then, we said that the other one, so we're going to plot. I need a line at 1. Now, if I put M, no, I don't know where it is. So maybe I won't put M. I'm going to call this something different, Let's call it, which one didn't I use? G, okay? So G is equal to 1. I guess it won't plot it for me. So let me use Y because Decimals uses the Y-axis. It doesn't know that I chose M. So this is what I have here. Okay, there we go. So this is how our plot looks like. Now, because we want to get it to 1 within here, so let's take a look and see. Okay, I'm going to zoom in here. So this is now at 1. Notice just so that you can see it. And here's my intersecting point. Okay, so I'm going to just plot that intersecting point with the other. So it takes about 9.4 days for that tumor, okay, to kind of go down in size from 670. I mean, that's quite a lot, right? From 670 just to 1, okay, or below. You obviously want to try to kill off the tumors as much as you can to have a successful, maybe, therapy. All right, so that's 5 examples, a pretty lengthy video, but I think it's worthwhile for students to be able to see these exponential functions in kind of some applications where you can say, oh, okay, I'm not just learning this, and all these videos that you're watching of me maybe doing these things, it's like, I don't know where the heck I'm going to use this. But it turns out that we can actually have some really good applications of it. And so here were 5 of them. All right. Okay, thanks for watching. We'll see you in a future video. Cheers, everybody. Hit a thumbs up if you liked it.